my first love was for the night sky. Love is complicated. You're looking at a fly-through of the Hubble Space Telescope Ultra Deep Field, one of the most distant images of our universe ever observed. Everything you see here is a galaxy, comprised of billions of stars each. And the farthest galaxy is 1 trillion kilometers away. As an astrophysicist, I have the awesome privilege of studying some of the most exotic objects in our universe. The objects that have captivated me from first crush throughout my career are supermassive, hyperactive black holes. Weighing 1 to 10 billion times the mass of our own sun, these galactic black holes are devouring material at a rate of upwards of 1,000 times more than your average supermassive black hole. These two characteristics, with a few others, make them quasars. At the same time, the objects I study are producing some of the most powerful particle streams ever observed. These narrow streams, called jets, are moving at 99.99% of the speed of light and are pointed directly at the Earth. These jetted, Earth-pointed, hyperactive, and supermassive black holes are called blazars, or blazing quasars. What makes blazars so special is that they're some of the universe's most efficient particle accelerators, transporting incredible amounts of energy throughout a galaxy. Here I'm showing an artist's conception of a blazar. The dinner plate by which material falls onto the black hole is called the accretion disk, shown here in blue. Some of that material is slingshotted around the black hole and accelerated to insanely high speeds in the jet, shown here in white. Although the blazar system is rare, the process by which nature pulls in material via a disk and then flings some of it out via a jet is more common. We'll eventually zoom out of the blazar system to show its approximate relationship to the larger galactic context. Beyond the cosmic accounting of what goes in to what goes out, one of the hot topics in blazar astrophysics right now is where the highest energy jet emission comes from. In this image, I'm interested in where this white blob forms, and if, as a result, there's any relationship between the jet and the accretion disk material. Clear answers to this question were almost completely inaccessible until 2008, when NASA launched a new telescope that better detects gamma-ray light. That is, light with energies 1,000,000 times higher than your standard X-ray scan. I simultaneously compare variations between the gamma-ray light data and the visible light data from day to day and year to year to better localize these gamma-ray blobs. My research shows that in some instances, these blobs form much closer to the black hole than we initially thought. As we more confidently localize where these gamma-ray blobs are forming, we can better understand how jets are being accelerated and ultimately reveal the dynamic processes by which some of the most fascinating objects in our universe are formed. This all started as a love story, and it still is. This love transformed me from a curious, stargazing young girl to a professional astrophysicist hot on the heels of celestial discovery. Who knew that chasing after the universe would ground me so deeply to my mission here on Earth? Then again, when do we ever know where love's first flutter will truly take us? Thank you.